In this video, we're going to talk about how much material you can dissolve into solution and its equilibrium constant and how it relates to solubility. Solubility is used mostly with ionic compounds because they are strong electrolytes. That is, they dissolve completely to some extent when they are added to water. Highly soluble compounds dissolve to a much greater extent than those with low solubility. However, they all have in common that they do break up to some extent and exist as ions floating around in water or some other liquid. When we write an equilibrium expression for solubility, we always have the solid and only the solid as the reactant, and then the products are the ions it dissociates into. The solubility product is the name for this equilibrium constant or equilibrium expression and is represented as Ksp. The solubility product and the solubility reaction shown here are for barium sulfate. We can see that we've written barium sulfate as a solid, as a reactant, dissolving into barium ions and sulfate ions. When it comes time to writing the equilibrium expression, we say that the equilibrium, or the solubility product, is equal to the barium concentration times the sulfate concentration. Note that there's no fraction here. By writing the solid as the reactant, and remembering that we don't include solids and liquids in equilibrium expressions, we don't have to worry about a fractional expression to solve for. Another example involves barium phosphate dissolving into barium ions and phosphate ions. And you can see here too, by writing the solid as the reactant, we don't have a fractional form in our solubility product expression. But other than that, it's the same idea that we're writing equilibrium constants being equal to products raised to their stoichiometric coefficients divided by the reactants, which in this case is a solid and 1. Now it's important to note that the solubility product is not the same as solubility. Solubility is the number of moles or grams that can dissolve into solution, whereas the solubility product is simply the product of the concentration of all ions in solution. We typically encounter solubility in terms of grams per liter or moles per liter. So when we calculate the solubility of something, we will have a solubility constant, and we will follow the same format that we've done before with our equilibrium expressions. Well, 1, write the reaction. For example, here calcium fluoride breaks up into calcium and fluoride ions. 2, set up the equilibrium, that is Ksp equals calcium times fluoride squared, and that's equal to 3.9 times 10 to the minus 11th. Then we go back to our ice table, and we can see for every calcium ion we have twice as many fluoride ions going into solution. Now we can set up and solve for what x is. That is 3.9 times 10 to the minus 11th equals x times 2x quantity squared. And remember, it's always a good idea to put the parentheses around anything that has more than a single coefficient for x. So in this case, 2x would be in parentheses raised to the power of 2. This way it reminds us to square both the 2 and the x. It's a very common mistake students make, is forgetting to square or cube the value in front of x. Solving for x, we find that we have a 2.1 times 10 to the minus 4th molar solution. That is, the molar solubility for this is 2.1 times 10 to the minus 4th, or 0.21 millimolar. In terms of grams, all we have to do is multiply this by the molar mass, and we find that the solubility is approximately 16 milligrams per liter of water. Weak acids and bases, the common ion effect will play a role in solubility. Ions can be affected by both pH and a complex ion formation. We'll talk more about complex ions in a minute. However, if one of the common ions is the ion of a weak acid or a weak base, then changing pH most definitely has an effect on the solubility. So too does the ions present in the soluble compound. For example, The solubility of calcium fluoride decreases as we increase the fluoride ion concentration. The more fluoride we add, the less calcium fluoride there will be in solution. This is one way we can use to drive out ions we don't want to have in drinking water, for example. We can drive lead out by adding something that causes the lead to come out of solution in the form of a precipitate. So if we expand our understanding of how to write an equilibrium expression, now with a common ion present, we can see that we can alter the calcium fluoride concentration in water in the presence of calcium nitrate. We still follow the same procedure, writing the equilibrium expression and setting up an ice table. Here you'll notice that the calcium ion concentration is 0.01 instead of 0 like it was in the previous problem. And that's because we have the calcium nitrate contributing some of its calcium ion to solution. We still see the same change in calcium and fluoride, and at equilibrium we have a slightly different equilibrium expression. Going through again, we can solve for the exact value of x, or we can make an assumption here. We can assume that x is going to be so small that it's essentially not going to change the calcium ion concentration. Therefore, we can leave it as 0.01 molar. Going through and solving for x, we now find that x is equal to 3.1 times 10 to the minus fifth, driving the concentration down significantly compared to what it was before. Other ways, like we've said, we can control pH control solubility by changing pH, provided that the ion is that of a weak acid or weak base and not negligible or a strong conjugate. Consider the two examples here where we have lead fluoride and lead 2 iodide dissolving in water. We can see that by changing the pH of solution for the lead fluoride becomes more soluble in water because the fluoride ion is the conjugate ion of hydrofluoric acid. Therefore, by adding an acid, we can actually increase the amount of lead into solution. The second case with lead 2 iodide, we find that increasing or decreasing the pH has absolutely no effect on the amount of lead 2 iodide in solution. That's because the iodide ion comes from a strong acid, hydroiodic acid, and that is a strong acid. Therefore, it does not change the iodide concentration nor the pH of solution when present in water. Complex ions also affect solubility. Now, looking at this table, you may feel it's a little intense to look at, but there's just a couple of things I want you to take away from this. One, the complex ions are driven by the dissolution of strong materials in water. Almost all of these ions present here will form a complex ion with water, although not just with water. Complex ions can form between multiple ions, as we see. For example, silver will complex with ammonia to make a silver-ammonia complex ion with a very large equilibrium constant. In fact, complex ions form because they have large equilibrium constants. They're driven to form. They form because there are lone pairs of electrons and places for electron pairs to be donated or accepted, and molecules and ions are going to take advantage of these opportunities to form these intermolecular forces, so that in solutions we have a lot of different complex ions floating around. As far as writing complex ion formations, you don't need to worry about that, but you would, for example, have to calculate what the silver concentration might be in a solution of silver and ammonia. We use these complex ion formations to help increase or decrease the solubility. In fact, we can separate compounds based off of the solubility and their formation of complex ions by altering the pH when they're in solution. So again, going back to that lead fluoride example, we could get lead fluoride to dissolve, and then at some point later on we could turn around and get it to precipitate out through the addition of something like ammonia. Deciding whether a precipitate will form is based off of the reaction quotient Q. When the reaction quotient Q is equal to the solubility product, then we say that the system is at equilibrium and the solution is saturated. That is, it's dissolved as much material as it's going to dissolve and won't dissolve anymore. When the reaction quotient is less than the solubility product, then it's a normal solution which we are used to, and so we can continue to dissolve whatever it is we have chosen to dissolve. That is, no precipitate is going to form at the bottom of our test tube or beaker when we're less than the solubility product. However, if we're greater than, the reaction quotient is greater than the solubility product, then a precipitate will form at the bottom of our test tube because the solution is well past the solubility point and can no longer accept any more ions into solution at that point.